¿Empezamos?
Supongo. No están los organizadores locales. Ah, chuta, yo creo que sí, han pasado 2 minutos.
¿Empezamos?
Sí, sí, gracias.
Okay, welcome to the afternoon session of today's lectures. Sebastián Herrero will talk about the Hecke orbits and equidistribution. Lecture third lecture.
Thank you. Okay, thank you. I just wanted to start by recalling what we did yesterday. So actually, in the first lecture, we defined these Hecke orbits in very abstract terms using elliptic curves, isogenies, or quotients by finite subgroups of order n. And then yesterday, we looked at this construction, but in the case where the base field is the complex numbers, and then we use the fact that the moduli space of elliptic curves over the complex is the same thing as this quotient space. And then we proved, we give an idea of the proof of the equidistribution of these Hecke orbits as n goes to infinity with respect to this hyperbolic, normalized hyperbolic measure, which is a measure which it's defined using this presentation of the moduli space. And as some people pointed out yesterday after the talk, this can be really stated about as a result about this quotient and the Hecke operators here, and you don't really have to define anything that comes that has anything to do with elliptic curves and isogenies. And also, like the limit measure, the measure that describes the distribution of the points, it really doesn't say anything about elliptic curves. It's just something that comes from hyperbolic geometry. But then if you want to do this p-adically and still kind of use this modular interpretation, we have to go back to the first lecture and think about moduli spaces. Because on this side, on the moduli space side, is obvious that we can take CP instead of C. But then we don't have something like this. Hence, we cannot use the hyperbolic geometry. We cannot use the hyperbolic Laplace operator, which played an important role in the proof. So we really have to come up with a different approach. Before moving to the p-adic setting, I just wanted to make a comment about something that was used in the proof. So we used the fact that there is a bound for the so-called Hecke eigenvalues on like for the Hecke operators Tn, which we defined yesterday also as operators acting on the L2 space. So we thought of these operators as acting on functions, and then we used that there was a discrete part of the spectrum with respect to the hyperbolic Laplace operator, and then we used that. So inside here, there was a special collection of vectors, and then these are called mass forms. And we also said that we can always take these mass forms to be eigenfunctions of the Hecke operator. So we got some eigenvalues, and we use a bound due to Kim and Sarnak. Which says that these numbers are bounded above by sigma 0n, the sum of divisors, times n to the 1/2 plus, what was it, 764. And there was a question of if one really needs this specific bound, and the answer was no. There's a trivial bound, which is when the exponent is 1, and there's the Ramanujan conjecture, which says that the optimal bound should be 1/2. So this is somewhere in between, and anything that is better than the trivial bound actually does it's good enough to prove the equidistribution. I just wanted to mention, like previous work by Kim and Shahidi, they got the bound. This is 2002. Kim and Sarnak was 2003, I believe. Yes, 2003. I'll put it here. And there was a bound of the form, so the same thing. But then the exponent here is 1/2 plus 1/9, which should be larger than this one. So this one is really an improvement. Before that, there was Bump, Duke, Hofstein, and Ivaniak. 92. They got n to the 1/2 plus 5/28. And I think one of the first bounds was given by Sev in 95. And this was like n to the 1/2 plus 1/5. So all of these are improvements of the previous bounds, and people in the area know that it's super important to get better and better bounds because it has a bunch of applications. I was just showing you just one of these, but as I said yesterday, Tuesday, for this equidistribution, you just need you can use any of these. I think at the moment when the paper of Closet and Ulmo was published about the equidistribution of these Hecke orbits over the complex, this was the best known result. And all of these use different techniques. Actually, the one, this bound from Kim and Sarnak used work of Kim about automorphic representation on GL5. So it's written in a different language. Anyways, I just wanted to show you a little bit about the history about this bound. Yeah, because people asked. Okay. And the other thing that I wanted to do is talk about the relation of this equidistribution of Hecke orbits to the equidistribution of CM points. So let me talk briefly about relation to special points or CM points, and also singular moduli. So let me just repeat some definitions that we already learned this week, but maybe I will present them in a different, slightly different language. So an elliptic curve over the complex, it has always the ring of integers inside the ring of all possible endomorphisms. So this is the ring of, if you want, the ring of isogenies from E to E plus the zero map. And this ring always contains the integers because you can always define multiplication by n. Recall that we defined in the first lecture the multiplication by n map. So you can always, inside this ring, look at the integers, and then it's a point in the moduli space is called a CM point if actually this is a proper contention, so there are more than just multiplication by n maps in this endomorphism ring, and it's a classical fact. Again, you can look at this book by Silverman, that when this is strictly larger than z, then this has to be a quadratic imaginary order. So this will be actually isomorphic in this case to, well, you have the integers, but you have something more. You have f times the ring of integers of imaginary quadratic field. So k, this I will call O df. So k here is q adjoint square root of d. D is a negative fundamental discriminant, so it's the discriminant of this field. And f is a number, an integer number, which is at least 1. It is called the conductor, but one has to be careful not to mix it with the conductor of the elliptic curve. This is the conductor of the ring of endomorphisms. So we have this nice description of these rings. And every time we fix this type of ring, we will get only finally many points in the moduli space that has exactly this ring. So let me define the following set. So every time I fix D and F, I can define all the CM points with this ring. So all the E elliptic curves over C, such that the endomorphism ring is given by this quadratic order, imaginary quadratic order, and this is finite. And I will use a notation for the number of elements. Here I will just call H df will be the number of elements here. This is not a very standard notation, but it's useful for, will be useful later. So this is a number that actually grows as any of these two quantities grow. So if we make D large, negative, or F large, positive, then this quantity will grow. So it grows whenever df goes to infinity. Any of the two quantities can grow, and this will have more and more CM points. And since we have a lot of points in the moduli space, we can again ask about the distribution properties of these points. And there is a famous uniform distribution result by Bill Duke. So theorem by Bill Duke from 1998. It says that he did it for fundamental discriminant when f is 1. So the sets lambda d1 are again as in Closel and Ulmos result, are uniformly distributed with respect to the same measure. So the normalized hyperbolic measure as d grows. And this was a very famous result by Bill Duke. And actually, the strategy of the proof, the first part is quite similar to the equidistribution of Hecke orbits. Again, you have to look at the L2 space, look at the spectral decomposition, prove the result only for mass forms and for Eisenstein series, or the piece of L2 that comes from this Eisenstein transform that I introduced on Tuesday. But then you have to use a deeper result about the values of mass forms over CM points and something related to the Shimura correspondence, and then a bound for the Fourier coefficient of certain half integral weight mass form. So it's another technique. Yep?
Yes, sir. You defined the D as the fundamental discriminant.
Yes.
And how do we get F from the elliptic?
Oh, so you get it from this ring. So F will always be the index. I will put it here. F equals the index. So you can have the maximal order, which is the OK. When F is 1, you get OK. In general, this is a smaller order. So this is just the index of this smaller ring inside this one.
Perfect.
But you get it really from the endomorphism ring, not directly from the equations of the elliptic curve, let's say, which is a different. The elliptic curve also has a conductor, which is a different number.
Right.
Yeah.
But from the elliptic curve,
Yep.
we can analyze the set of endomorphisms and
Yes.
have this conclusion.
Yes. You can also, if you have the complex uniformization, you can look at this as E as a quotient of C mod the lattice, and then you can look at the complex numbers that, when you multiply lambda, this is contained in lambda. And this is exactly the collection of those alphas. That's why it's called complex multiplication. It really comes from the fact that there will be a lattice that you can multiply complex numbers against the lattice, and then you will still be inside the lattice.
Perfect. Thank you.
Okay. Yeah,
Question.
so,
If
yeah.
you fix D and let F go to infinity, do you get equidistribution from Closel-Ulmer?
Yes, exactly. It's exactly what I was going to say. Yeah, but this is how Hecke orbits play a role here. So the original result is in this form, and then I think the original motivation of Closel and Ulmer to study, one of the motivations to study the equidistribution of Hecke orbits is that now you can do the general discriminant case by applying Hecke operators. Exactly. So it's exactly so. Let me just say then that. Let me just put this in a square and just say that for f at least 1, for any f, essentially we have that the collection of all CM points of general discriminant and general conductor for the ring of endomorphism is essentially, I'll put it in quotes, it's more complicated than that, but you can essentially apply the f Hecke operator to these points. It's a more convoluted expression, but essentially the main contribution comes from the TF operator acting on CM points of fundamental discriminants. That means that now you can move the F and use equidistribution, moving the F here. There is the theorem of Closel and Ulmer, and then you get as a corollary, you will get that in general the sets lambda df are also uniformly distributed with respect to the same measure, of course, as now d times f goes to infinity. So you can vary any of these. Okay. And now that we have the general uniform distribution of all possible CM points there are some arithmetic consequences for singular moduli. This is another kind of famous, I would say, result by Habeger, where he applied this uniform distribution result of CM points plus some other results, some other properties of CM points. He proved that there are at most finitely many singular moduli that are algebraic units. So let me quickly recall that singular moduli was the J invariant of a CM elliptic curve. So this one is a CM elliptic curve, and this is by classical theory of complex multiplication. This is an algebraic integer. And then we are saying that we can ask if this number can be a unit in this ring. Which is kind of, it's related to this result of Gross and Zagier, right? This work of Gross and Zagier that we saw on the Monday. It was about the factorization of the norms of singular moduli, and then we saw that you can have like small primes but big exponents. The question was, in that setting, is like, can you have norm equal to 1 or minus 1? And then the first result in this direction was this theorem by Habeger, which says that there are at most finitely many exceptions. This result was not non-effective because there is kind of a problem in this uniform distribution result by Duke. You need to use a lower bound for the class number for imaginary quadratic fields, and we only have a good lower bound which is non-effective, which is due to Siegel. Okay. So this was one application of equidistribution, but now I should say that now we know better. There are actually no singular moduli that are algebraic units. So this set is not just finite, it's empty. There's another theorem. I will write it here. And this was by Bilu and Bilu, Habeger, Kuhne in, when was this? 2020, and by a very different approach by Yin-Kun Lee, 2021, so almost simultaneously. The result is that no singular modulus is a unit, is an algebraic unit. So in these tables of norms of singular moduli, you will never get a 1. And it's also true for differences of singular moduli. This is actually contained in Lee's work. Okay, so even though this last result that I'm describing here doesn't really rely on equidistribution, still the first result of Habeger does, and it's just the way mathematics evolves. Okay, so this is just to give you an idea of what kind of applications you can get. And finally, I want to move on to Hecke orbits over CP. Where we will see that the situation is quite different. So there is a new phenomenon that occurs in this setting, because in this setting we can always take reduction of elliptic curves. So this will play a very important role. So let me talk briefly about reduction of elliptic curves. So the first thing that I should say is that any elliptic curve over CP maybe I should just quickly say that CP is just the completion, what is this? Completion of the algebraic closure of QP. So it's like QP, like this, and like this, I guess. It's like algebraic closure and then metric completion. It's a huge space. It has really bad topological properties. Still, you have ring of integers, you have a maximal ideal, and you have a reduction map. So you have OP will be inside CP the ring of integers. So this is, I will just probably define it. So any E can be defined over the ring of integers as a projective curve. So OP is, by definition, the ring of integers will be all the elements in CP, which have norm at most 1. This is a very simple fact because everything is projective. You can always construct an equation defined over this ring. And then we also have the maximal ideal, which is all the elements which have norm strictly less than 1. And we have this projection map that goes from OP to OP mod MP, which is an algebraic closure for FP. So that's how we are going to go from elliptic curves defined here to elliptic curves over FP bar. And then over FP bar, there are different types of elliptic curves. So this is where this type of reduction appears. So given any E can be defined over OP, hence can be reduced mod MP to get some curve E tilde over FP bar. But we have to remember that the definition of an elliptic curve is like, you can really put a Weierstrass model and so on, but you always need this curve to be smooth. There was this condition about non-vanishing discriminant. And in this case, it might happen that, let's say, P divides the discriminant. So when you do the reduction mod P, it might be discriminant 0. That will mean that this curve is singular. And in particular, that means that this is not an elliptic curve. So sometimes this is an elliptic curve, sometimes it's not. So we have this first dichotomy. So we have bad reduction if E tilde is singular, it's not smooth. And of course, we have good reduction. But also in the good reduction case, we are going to distinguish two subcases. So this is E tilde is indeed now an elliptic curve over FP bar. But elliptic curves over FP bar come in two different flavors. You can have ordinary reduction, can be an ordinary elliptic curve, or can be a super singular elliptic curve. So ordinary, there are several ways of defining these things. Ordinary will mean that, I will use the following, I will use that the endomorphism ring of the reduced curve, it's again one of these imaginary quadratic orders. So will be isomorphic again to something of the form ODF as before. And so here, like all of these are like CM elliptic curves, even though the first one doesn't have to be an elliptic curve with complex multiplication. It can be anything that has a trivial endomorphism ring. But in the reduction, it will have this, or it can have an endomorphism ring that is even larger. So it might happen that the endomorphism ring of the reduction is actually a maximal order in this quaternion algebra ramified at P and infinity. So will be larger because it will have rank 4 in the second case, and the first case it only has rank 2.
Sorry?
Yeah? Yes. Yes. And actually all the super singular elliptic curve they give you all the maximal orders in this quaternion algebra up to conjugation. So this is a maximal order. And then, as I said, B p infinity is the unique, what is this? Quaternion division algebra Q algebra ramified at P and infinity.
Question.
Okay. Yes.
Well, if you go over QB, you usually take like the minimal Weierstrass model, and
Yes.
then there's well-defined and unique, but there's no minimum. I mean, there's no discrete valuation of you.
No, you just say like among all the models, if for this smooth or non-smooth condition, you mean?
Yeah, like when you call it bad reduction, if
So in this case, it's actually quite, I can give you a very easy criteria to decide when something has bad or good reduction. If the J invariant has p-adic norm larger than 1, it will be bad reduction, because basically you cannot reduce the J invariant. If it has J invariant in OP, it will be good reduction. And the reduction of this number will be the J invariant of the reduced curve.
you can find one.
Yes, you can find one, yes. But indeed, there's no minimal, there's no local field here. Yeah.
If you did it over QB, you might have to twist.
Oh, you don't find it over QP itself.
Or you can have a curve that is bad reduction at P, but
Mhm.
it becomes good for the
Yeah.
field extension.
Exactly. Here we forget about this potential good reduction and so on, because everything is at the end you go to algebraic extensions if you need, because we are working over CP. Yeah.
So here everything is good or multiplicative.
Exactly. 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 Yeah. Okay. So this distinction of these three types of reduction, they give us a decomposition, and first a very abstract decomposition, but nevertheless a decomposition of the moduli space into three disjoint pieces. The first one will be elliptic curves with bad reduction. Then you have the ones that have good reduction but is ordinary. And the third part is good reduction but super singular. So this together is good reduction. And this bad reduction. And let me give you an idea how these different sets look like. We are going to use the fact that we can identify this moduli space with the base field using the J invariant. This is what we said in the first lecture. And this is basically the only thing that we can do. We don't have this complex uniformization theory, so we can only use the J invariant. And then what's going to happen is that the bad locus, so this is the collection of all points which have bad reduction, will correspond to the complement of OP, so will be CP minus OP. And this is exactly what I was saying before. This is all the J's which have norm larger than 1. Hence, you cannot really take the mod P, the mod MP reduction of this, or it goes to infinity if you want. And then for the other two pieces, I can also give you a brief description. So this is one thing. And the other thing is that there are finally many residue classes B1 to Bm, some m. And these are residue classes for the projection map, for the map that goes from OP to OP mod MP, which is FP bar, this natural projection map that I wrote somewhere here. There are finally many residue classes such that the ordinary locus will correspond to OP minus the union of these residue classes, and the supersingular part, of course, is what is left, which is the union of these ones. And of course, these residue classes correspond to, these are disks that reduce to the J invariant of supersingular elliptic curves, which we know that over FP bar, there are only finally many of these. So here M is just the number of E elliptic curve over FP bar. And I will always use a small e for elliptic curves over positive characteristic. So these are the supersingular ones. And this number is kind of like p minus 1 over 12. I can be more precise, but just need that there's finally many of these. And it's always positive. There's always at least one supersingular elliptic curve for every p. OK. And now the important fact, the reason why I'm introducing this trichotomy of the type of reduction is that Hecke orbits stayed in the same region. If I start, let's say, if I start in a point which has bad reduction, then the Hecke orbits will be contained here. And the same thing for here and here. That means that there's no way we are going to get any kind of uniform distribution over the whole moduli space by this simple reason. It's really like 3 different spaces, and then you have to study the Hecke orbits on each one of these subspaces. So fact, an easy fact to show that, so if I have 2 elliptic curves over CP, then that are isogynous. So if I have 2 points that correspond to elliptic curves that are isogynous, then they have the same type of reduction. And since Hecke orbits are exactly giving isogynous elliptic curves to the first one, then this implies what I just said, that we will always stay here, here, or here if we start with a point which is here and here and here. So no way we will have some kind of measure defined on the whole space, at least that is supported on the whole space, that will give us the asymptotic distribution of general Hecke orbits. So we will have to do one case at a time. So here I want to give a reference where this p-adic distribution of Hecke orbits is described. This was done with Ricardo Menares and Juan Rivera Letelier in 2 different papers. It's called p-adic distribution. And as I said, we cannot no longer talk about equidistribution, it's just distribution of CM points and Hecke orbits, so CM and Hecke points. And there's like part 2 and part 1 and 2. So part 1 and 2. There are 2 papers. Okay, and for the rest of this mini course, I just want to give you an idea of the techniques that are used in each case. The most interesting and I would say complicated case is the supersingular reduction case. The first 2 are rather, it's not so difficult. once you know the answer, I guess. So let's do first the Hecke orbits on the bat reduction locus. Let's see time. Okay. So here we can kind of use uniformization theory, but it's a different kind of uniformization theory. It's multiplicative now. It's what is called like Tate uniformization. So we have given a curve with bat reduction. There's the so-called Tate uniformization theory that only works here. Says that if I look at this as a rigid analytic space, then this is like Cp star mod Q to Z, where Q is some element in this maximal ideal MP, which is non-zero. And this is basically what you get also in the complex setting. If you take this complex uniformization, C mod lambda, and then you apply the exponential map. If you write lambda as 1 generated by 1 and tau, you apply the exponential map. The complex plane will become C star, and then the Q will correspond to E to the 2 pi I tau. So this is a multiplicative version of that. And here, there's this really nice relation between the J invariant and the Q is really given by the Q expansion of the J function, which is we also saw some days ago. So here the J invariant of this curve will be exactly 1 over Q plus 744 plus, it will be an infinite series. What was it? 1968, 84, Q, blah, blah, blah. Some infinite series. This is the relation between the Q and the J. And here you can see using the ultrametric triangle, the fact that the p-adic metric is ultrametric, that the J invariant here is given, the p-adic norm of it is just norm of Q to the minus 1. And that's why we get a J invariant which is larger than 1, because Q has p-adic norm less than 1, which is as expected, because I said that elliptic curves with bat reduction have J invariant which is larger than 1.
For NP
Yep.
is the maximal ideal?
This is the maximal ideal of OP.
All right.
Yeah, is the open disk. It's open, and one has to be careful with that. But the elements we have norm less, strictly less than 1.
Perfect.
So using this nice description of this elliptic curves with path reduction, we can play the same game we played in the complex setting, which was to then translate the action of Hecke operators, but now in the language of Tate curves. These are called Tate curves. So let me put a name. I think orange was bad, so let's use purple. This was Tate of Q, this quotient. And then we can use that the Hecke correspondence or operator acting on the Tate curve. It has the following description. Remember that this was defined as a divisor. I have to sum over all these positive integers, which are divided in n, and then I have to take all possible t in MP that satisfy the equation t to the d equals q n over d. So there will be d possible choices for t, and then for each choice of t, I put the Tate curve. So it's very concrete, very explicit, and you can compute the J invariant of this one easily using this formula. Well, at least the p-adic norm will be easy. And then what we get is the following. So recall, again, that the bat reduction locus corresponds or can be identified with the complement of the unit disk. So these are all the elements of norm larger than 1. So let me write it as Cp minus OP. And this one allows a simple cover by open sets. I will just put this as a union as n from 1 to infinity of a given, let me see the notation that I use here. This is a neighborhood of infinity, center at 0 and radius r. So this is by definition all elements set in CP. Sorry, this is wrong. Should be r larger than 1. So I will use this as a cover of the whole space. So if I look only at those elements which have norm larger than r, and I take the union over all possible r, thinking that r is kind of convergent to 1, then this will give us a cover, an open cover of this space. And then we have the following theorem. Which says that if I compute, I want to look at the Hecke orbit of a point with bad reduction, and using this formula, we get that the number of points which lie in one of these disks, so I will just look at the points in the Hecke orbit which lie on this disk for any positive r larger than 1. And now what I'm doing is just looking at this divisor, only taking into account those points which lie in this disk. And now I compute the degree so that I'm counting how many points I have here. And then I divide by the total degree of this divisor, which was sigma 1n. What's going to happen is that this goes to 0 as n goes to infinity, which means, in other words, that the proportion of points which are in this disk is going to 0. So I will try to draw a picture. So OP, even though p-adically this is a really bad picture, but if this is OP, if we think of it just as the unit disk, what we are doing is taking kind of a neighborhood of this, and we are saying that the points which lie outside, the proportion of those points goes to 0 compared to the total degree. So it's kind of saying that the points should kind of converge to the unit disk, even though that doesn't really make that much sense in the p-adic setting. So this might look like a very weird statement, or
Right.
yeah.
What means a 6 star into a Q to C? To set
This one?
Yes.
Oh, okay. So this is just the non-zero elements in CP. Q is a number, and I'm taking all the products of all the powers of this Q. Okay? This will give me a discrete subset of this. So I'm taking the quotient space. It's really similar to this torus construction. They take C mod a lattice, but this is a multiplicative version. Yes?
Is that Q unique?
Yes. Yeah, there's a correspondence between this MP minus 0 and the bad reduction locus.
Invariant, should all the Qs with the same absolute value should give the same?
No, because this is just the p-adic norm of J.
Ah,
Yeah, and J is the number is the invariant, not the norm.
Sorry,
Yeah, yeah, no worries.
sorry.
Yeah.
Maybe a quick follow-up. Is that restriction or quotient you're doing?
This one?
Yes.
Sorry, it's a quotient. It's a quotient, really a quotient. Yes. Mod. Let me put it like this. Yeah, it's a quotient. Again, it's like this is multiplicative p-adic version of a complex torus. Yeah. Thank you. Okay. So, how much time do I have left? Not much. Okay. So this looks maybe as a simple, just counting asymptotic, but the reason why that I chose to present this result in this form is because this is somehow a more naive statement, which is equivalent to a more sophisticated statement, which is I can rephrase this theorem in terms of convergence of measures, the same way we did it in the complex setting, but now I have to use something called the Berkovich affine line. So as I said in the first lecture, the CP is really a bad topological space. It's really, it's not locally compact, it's not connected. There is really a measure theory in CP is not good. So instead of that, one has to work in a bigger space, which has better analytic properties. And this is what people do, for example, in dynamical systems. They usually don't do dynamics over CP, but they look at this Berkovich space. So let me introduce quickly the Berkovich affine line. What was the notation here? A1 Berk over CP. So there's an abstract definition that doesn't help much for intuition, but I have to present it in some kind of formal way. So let me just say that this space is, as an abstract space, will be the collection of all maps from the polynomial ring. Oh, this is a terrible notation. Shoo. What were you said you were using, right? Yeah, set. Let's do that. To R plus 0, and this will be multiplicative maps. And these will be actually seminorms. So they satisfy some triangular inequality. And actually, we'll ask this seminorm to extend the p-adic norm, because inside this polynomial ring, we have CP. And then what we are doing is that this map over constants will be the same thing as the p-adic norm. So this is an abstract definition. And then there's a topology on this space. The topology on this Berkovich affine line is the weakest topology, making the following maps continuous. So for every time I fix a polynomial, let's say P is not a good letter, F. Every time we fix a polynomial, the map that goes from A1 Berkovich to R plus 0, that sends an X, and X, it's a point in this Berkovich space, but it's defined as a map. So I can evaluate X at F. Sorry, I think I made a mistake in this definition. Is it? No, I think it's fine. Multiplicative seminorms and then this. And this has to be, I guess this is, no, it's fine, it's fine, sorry. This has to be continuous. So basically the evaluation map has to be continuous for every time I fix a polynomial that I use to evaluate my seminorms. Okay, so this gives some kind of weak topology. Fact about this space is that this space with this topology has a very good topology. This Hausdorff is locally compact. It is also path connected. And of course, this has to be some kind of completion of CP, because we were working over CP. Now we are working on this abstract space. And indeed, one can see that this is an extension of CP, because there is a natural map. There is a map iota that goes from CP into A1 Berkovich, which is simply, it sends, now I have to choose a different notation, whatever, y goes to iota y. And what is this? This has to be a map from CP set to, from polynomials to real numbers. And this will be take a polynomial f, no, can I use f? Yes, f, and send it to the polynomial evaluated at this point, and now take the p-adic norm. So this is an injection, and actually the topology of the induced topology on CP using the topology of the Berkovich affine line is the same as the original topology of CP. So it's really, we are topologically embedding CP into a huge space. But now this space, it's very nice. For example, we can connect two different points in CP, even though CP is it's not path connected. We can connect 2 points through the Berkovich space. And I think there's this very nice analogy with the upper half plane. If you think of Q as being a really bad topological space, it's also totally disconnected. So you put like a bunch of points. And then you think of H as some kind of completion, because every time you take 2 points in Q, which you cannot connect through Q, you can connect them through the hyperbolic plane. So it's a similar picture, similar idea, just p-adic now. So H is like, it adds these geodesics to connect 2 points, and this has nice analytic topological properties. Okay, so I have introduced this abstract Berkovich space. There is a special point which is called the canonical point in the Berkovich affine line. We will write it X canonical. And this will be a point which is in this larger space, but is not a classical point, does not come from this embedding from CP to the Berkovich line. And this is given by the so-called Gauss norm of a polynomial. So this guy, again, by construction of the Berkovich affine line, has to be a map that goes from polynomials to reals. And what it does, it takes a polynomial, f, which has some, I can write it as coefficients, right? A, I, Z, I from 0 to something. Then it will be mapped to the maximum among the p-adic norms. So A0, A1, and so on. AM. So it's the maximum of the coefficient. It can also be computed as the supremum of the p-adic norm of the polynomial evaluated on, can I use that? Y, I would just Y. Over the unit disk. So this is a supremum norm over a disk. And in general, for every disk that you have, every closed disk, you can define the supremum over that disk of the p-adic norm of a polynomial. This will define a point in the Berkovich space. So in general, if you have a B inside CP, which is a closed disk, closed in the sense of non-strict inequality, then that defines a point XB in the Berkovich affine line by the same construction. Just take the supremum over B. So this is the point corresponding to the unit disk, as I said. And then why does this help? Because now we can think how this works. How can we connect two different points? Essentially, every time you have 2 points, let's say y1 and y2 in CP, you can think of this as generated disks, so disks of radius 0. So you can think of these points as the disk of center y1 and radius 0, the closed disk, so this will be like this. And the same thing with this, with this kind of inequality. And then they are two different points, but if you start increasing the radius, we know that in complex geometry, two disks are either disjoint or one is containing the other. So there's this weird phenomena that they are disjoint, 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 and at some point they touch, and once they touch, they are exactly the same. So they can be joined by increasing the radius.
Sorry, xb is defined as the supremum of y
Yes.
varying b
Yes,
of
sorry.
this function.
So xb of a polynomial f will be the supremum of the p-adic norm of the polynomial evaluated at some point in B. Yeah, it's the supremum norm associated to the disk.
Thank you.
Yeah. So when B is just a point, it's just evaluating the polynomial at the point and taking the p-adic norm. Okay.
Thank you.
So this gives an idea of how this can be seen in this Berkovich space. So I said that you can join two points by just increasing the radius until the disks become the same, and you will have like 2 points, y1 and y2, which in the Berkovich affine line, they will connect like this. And actually, this one has a structure of an infinite tree. So that's the idea. It's not really precise. One has to be more careful because not all the radius are allowed, but just to give you an idea. And now I will finish just by restating the kind of naive result that I presented, which was just counting a proportion of points which were outside some disk. So we have the following result. So the theorem can be rephrased. I don't know why I put it in this order. Okay, sorry. And then the result is that, again, for every curve with path reduction, if I look at this was, remember, the probability measure associated to this divisor, so just put one direct measure for each point in the orbit, in the Hecke orbit, and then you take the average, so divide by sigma 1n. This will converge as n goes to infinity to another direct measure on the canonical point. So this is on the Berkovich space. And this, again, as before, weakly. So somehow this can be stated as a convergence of measures, but this measure is no longer supported on CP. It's supported on just one point in this larger space. So you really you don't see the distribution kind of properties of Tn just looking at CP, unless you state it in this naive way as I did it in the previous theorem. And tomorrow we will finish this mini course by looking at the other regions, the ordinary reduction case and the supersingular reduction case, and we will see that in the supersingular reduction case, you don't need to go to the Berkovich affine line. You will have some other measures that will describe the asymptotic distribution. So it's really, it will be different from this case. I will stop now. Thank you.
Questions?
Yeah, so just to clarify, so this
Yeah.
theorem surely is much stronger than the previous theorem you stated. They're not equivalent in some way.
Should be equivalent.
Because if the points kind of go onto the boundary of this bad disk, they could still conspire to have similar p-adic digits, and then we wouldn't converge to the Gauss point.
Say again, can you repeat that? So
Well, if the points, you kind of show that the points go out to the boundary, as n goes to infinity.
they go from outside to approaching to the boundary.
depending on
Yeah,
whether you
yeah,
use
yeah,
K
sure.
or Q,
Yes.
But it's sort of to the boundary.
Yes.
But then they could still lie kind of on the same side or something. Whereas here, this result seems to imply more that they equidistribute along the circle, so that the measure that you get from them is really the Gauss point. Or are they really?
I think they're equivalent. Yeah, because maybe because it has to do with the weak topology of the Berkovich affine line. But I remember like these sets that I was describing, this BR, they are a basis of the neighborhoods for the Berkovich. they correspond to a basis for this, what is it called? System of neighborhoods of this point in the Berkovich-Affine line.
Maybe I missed something important. What was the center of the disks? I didn't write it down. I thought it was always the same point.
It was 0, yeah.
Ah, okay. So
It was 0.
don't understand.
But it doesn't matter, right? If you move, I mean, p-adically, if you move the center, it will be the same disk.
Yeah, but anyway, maybe we can talk about it
yeah,
after. I'm a bit confused.
because now I'm confused
This
also.
seems stronger. But
Um,
I'm probably missing.
Maybe there's a subtlety here, definitely.
Yeah. You picked 2 points in CP, right? And then started considering it as a ball with
Yeah.
radius 0,
Yeah.
right?
Yeah, exactly.
And then you increased the radius so that all balls are equal.
At some point, they are equal. They are exactly equal when the radius is the distance between the points, right? That's the exercise.
The problem is that, at least in Euclidean geometry, if you have 2 different points in balls, yeah, center it in it, the radius must be infinity to get exactly the
But
same.
this is something that happens only in the p-adics. It's a consequence of the strong triangular inequality that 2 disks in CP, you have like B1 and B2 inside CP, and let's say they have the same radius. So you only have 2 possibilities. They are disjoint,
All right.
or they are the same. This is something that once they touch, it's like they just collapse. This is something that happens only in this rigid geometry, this p-adic setting. And they will always, if you take this radius for both disks, exactly the distance from y1 to y2, this is exactly the moment where these 2 disks touch, and then they become the same.
Perfect.
It's difficult to explain geometrically because it's so weird in this p-adic geometry.
Perfect. P-adic geometry is far away from Euclidean geometry.
Yes,
Perfect.
yes, that's very different from Euclidean.
Thank you.
Sorry.
So maybe 2 things. So is there any advantage of considering the projectivization of A1 in the Berkovich sense when dealing with this bad reduction locus?
Not really. I mean, definitely you can look at P1 Berkovich. But since we are just, I would say no, that you don't gain anything. Everything is in here, and the convergence is because the convergence is to a point which is already here.
I see.
Yeah.
So you don't have to worry about
Yeah, exactly. But for like people doing dynamical systems and so on, they usually work with P1 Berkovich. Also because they work, let's say, with rational functions and so on. So you need to include infinity in your analysis.
I see. And can we consider AM Berkovich if we're trying to deal with higher abelian varieties in this context?
I guess so, yes. I guess so, yes. I don't know. This, I don't know. Yeah, I don't know. I don't know about much about general Berkovich spaces. This is the one that I had to learn about because of this problem. But yeah, I mean, there's a whole theory of Berkovich spaces, so I'm sure you can do it. Yeah.
Thank you.
Yeah.
Oh,
So
that-
also along this line of question, so you said, I understood correctly, if you take 2 different Qs in M, then it
Yes.
gives you different
Tate curves, yes,
different elliptic curves.
yes.
But now if you take something from A1 Berkovich,
Ah.
it's not in CP, does it also define your elliptic curve?
I don't know what it defines because really we are going outside the moduli space, right? So this,
I don't know,
yeah, no, I don't think so. I don't think there is like a moduli interpretation of the points in the Berkovich space. I guess that's the question, right?
That's the question also, if
Never thought of
there's
it.
an identification and if there's a modular CP.
No, I mean, I always think of points in Berkovich, in the Berkovich affine line either as classical points or these points that come with these disks. So they will correspond to disks of elliptic curves in a way.
Right, okay.
Yeah.
More questions?
Patricio?
When you have 2 curves with their Tate uniformization,
Yeah.
how do you detect if they are connected by any such entity?
How they are connected? It was hidden in the formula that I was given. It's like an algebraic equation, right? I wrote that one of them raised to the power d equals the other one to the power n divided by d. So that's hidden in that formula was the connection, like how to say when one Tate curve is isogenous to the other one.
Is there something similar like in the complex case where you isogenes are like to multiply by lambda a complex number that sends one.
I guess it's the same because it should be the same because yeah, is it? I guess. I'm guessing this formula for Tate curves is the same for the complex. It's just that the J invariant is no longer just norm of Q to the minus 1. So it's not like the Q uniformization maybe doesn't help to study the distribution of Hecke orbits on C.
Okay,
Maybe,
more
maybe.
questions? If not, we thank you here.
So you were asking about kind of the angle,
2 questions. Yeah, exactly.
but
That's what I. So can I just clarify in your picture? Your first theorem. So if you draw your Berkovich space, the usual sort of set.
yeah.
So this is now my disk at infinity. Infinity being the value of the J function. And so this disk parameterizes all of the bad elliptic curves.
Okay.
And you've now extended it to this A1 Berkovich.
Yeah.
And so can I just clarify, your first result that you stated, was it of the form that if you take any disk around here with some fixed radius, and now you hit Tn to your curve with bad reduction, then eventually you will go outside of this disk. Was that the result? In other
Outside-
words, the points kind of move out to the boundary of this disk.
of
as
the
n
unit
goes to
disk.
infinity.
Of
Is
the
that
unit
what you
is
proved?
yes.
I see.
Yes.
But then I don't understand how, because this seems stronger. It could be that all the points that you push out with your Tn of your bad elliptic curve,
Yeah.
that they all sort of conspire onto one side of this picture. Somehow. That they all go to the boundary, but they have a tendency to all go there. For instance, if you expand them as a p-adic number, they all have the same first 100 digits or something, and then after that they will. Could something like that not happen if you know your first theorem?
But why does this one imply that this does not happen?
Yeah, so this would exclude that, because you see, if you take all the points here bunched up, then the thing it would converge to would be sort of the point. So if you go up in the tree here to the point, the minimal point that sees all of these points, this would be the point that you converge to. So in other words, kind of the supremum of the disk where these guys fill up in some sense. But you're proving, no, it's not that, it's this guy, if I understand correctly.
Yeah. Should.
Isn't this point the only one that is close to every outer?
Well, I don't think so.